All right, so we'll continue to talk about the system of linear equation and the application of matrix algebra on that. Um, so where were we? So going back to the basic, so basically we want to solve a times x equal to b. So this is in the real space, right? So we know the answer is x is a inverse times b when a is not 0, right? So there are many question marks. So first we need to know what a inverse should be in the part of a matrix algebra. And we also need to know what will be the condition, what will be the similar condition to a equal to not 0 in the matrix algebra. So before doing that, we'll first introduce the zero matrix. So 0 is well defined in the real number system, right? So we know what 0 is. So I'll make a table of the similarity and differences between the real number system or the linear equation in real number system and the linear equation in uh, n by n space. So zero matrix is typically written down as, so this is the zero matrix. So in three-dimensional space, so I mean, I don't know how to write the boldface. So when I want to write down the boldface, I put this underscore, okay? So this is boldface. You know what boldface is, right? No? Yes? Yeah, I mean, like, so I want to write down this boldface, but I don't know how to write it down. So I'll just, or I'm lazy, so I'm just going to write down this way, okay? So this is the zero matrix. And the reason this is the zero matrix is in real number system, we know that a plus 0 is 0 plus a is a, right? So this is a special characteristic of a 0 in real number system, right? So you add it in any way you like to a number, then it spits out the original number, right? So with this matrix, we're going to have the same property that you add any matrix, it's going to spit out the original matrix. All right. Now we need to define what 1 is in the matrix algebra. So we sometimes write down this way. So this will be the 3 by 3 1 matrix. And there's a special name for that that is called identity matrix. Okay. So you can imagine what the matrix will look like in a 2 by 2 matrix, right? In a 2 by 2 matrix space, that will be this one, right? If it's 4 by 4, we will have a 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, right? So I'm just going to use a 3 by 3 matrix as an example, but it's not limited to 3 by 3 matrix. So what is A? What does A do in real number system? What's the characteristic of 1 in real number system? That is, you multiply 1 to a certain number or multiply the other way around, it gives you A, right? So the same thing is going to happen here. So you multiply a matrix then it's going to spit out the same number. So we can check it. So 1 0 0, what does it give you? What does it give you? Yeah, it gives you A1 1, right? And you multiply this one, what does it give you? A1 2, right? So you multiply 1 0 0 with A1 to A2 to A3 2, you get 1 A1 2, right? And the same thing for A13. And if you multiply 0, 1, 0 to the first column of the right-hand side, what does it give you? A21. And you multiply with the second column, what does it give you? That gives you A22. And you multiply to the third column, that gives you A23. And if you multiply 0, 0, 1, everything's okay? Yeah? That gives you A31, A32, A33. Okay? So it spits out the original matrix. And it's not just the left-hand side multiplication, the same thing happens to the right-hand side as well. I get the same result. So here you multiply this with this, A11. You multiply this, oh, it is not the, so you multiply with this one, then you get A21, and you multiply this one, then you get A31, okay, and so on. Okay, so it's gonna spit out the same number. So this is the equivalent to number 1 in the real number system. Okay, so this is the identity matrix. So what else? So now, where are we? How far did we go? Let's see. Identity matrices, zero matrices. All right. So in real number system, so these are just the counter examples. So in the real number system, a times b equal to 0 implies a is 0 or b is 0, right? Okay, so you know that, right? So if a times b is 0, either a or b is 0. But that's not really the case in matrix algebra. So I'll give you an example. So matrix 2, 4, 1, 2, matrix minus 2, 4, 1 minus 2 equal to 0, 0, 0, 0, right? So you can verify that. So you need to verify this one, okay? So if you multiply these two matrices, we end up with a 0 matrix, right? So, 2, 4 minus 2, 1, we get minus 4 plus 4 equal to 0. 2, 4, 4 minus 2, that also gives you 0. 1, 2 minus 2, 1, that also gives you 0. And 1, 2, 4 minus 2 also gives you 0. All right. Let me see if it's recording correctly. Yeah. All right. So clearly the multiplication is 0, but that doesn't mean that one of them is 0, right? So we break the similarity breaks down here. Okay. So matrix algebra is not exactly the same to the real number algebra. Okay, so it's not exactly the same. Similar to this, we know that if A times B is C times B, then we know that A is C unless B is not 0, right? Okay, so in real number, we know that, right? So again, this is not going to be the same. All right, so because I can rewrite it as A minus C times B equal to 0, right? All right, so I should say this way. So A matrix A times B equal to matrix C times B does not mean that A is a C. Okay, so it's very easy to show because the same equation is the following, right? So we know that this is not necessarily 0. So in other words, A is not necessarily C. Okay, so this is so it's basically the same phenomenon. Okay, so what I mean. So for example, I can cook up the example like 3, 5, 2, 3, and the C is 1, 1, 1, 1, and the B is -2, 4, 1, -2, and this will show that A times B is the same as C times B, but they're not going to be the same. Okay, so we can bring most of what we know from the real number system to the matrix algebra, but not all of them. Okay, so that's where the difficulty lies. All right. So so before defining the inverse of a matrix, all right. So before defining the inverse of matrix A, uh, we'll figure out what kind of properties we have. So the first of all, we define the transpose, or sometimes it's written down this way. So that is a transpose is AJI. So this is the definition of a transpose. So in this current textbook, the author is using A prime for the notation of a transpose. But I prefer this notation, but neither of them is perfect. But anyway, so what does it mean? So that means if, for example, if A is 1, 2, 3, 4, 5, 6, 7, 8, 9, then transpose is 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see what it is, right? So it's like using this axis, you're flipping it. You're flipping the matrix, all right? So along this axis, you're flipping it. So that's flipping is called transpose of a matrix A. You'll see why this becomes important. Um, so some of the properties we know of the transposes, this is clear, right? So transpose of the transpose is the matrix itself, right? It's like a flipping it twice. See what I mean? So you're flipping the matrix along this axis once and twice, then becomes the original matrix, right? So that should be easy to prove. And transpose is so-called a linear operator. Okay, so the transpose of the summation is the same as the summation of the transposes. All right. So this seems trivial, but you need to prove it. Okay, this is a little bit non-trivial, but this is true. Okay, so how do I know that? So proof goes like this. So define C as the A times B. Then C transpose is going to be CJI, and the C is going to be CIJ, right? So when C is I is index for the row and J is the index for the column, for CT the indexes are reversed, right? So first row second column becomes second row first column, right? So this is what I meant by writing this way. So the proof is very trivial that Cij is the summation of Aik Bkj, right? So this is something we already know. So but multiplying Bt times At So let's define, let's say this is D, all right? Then Dij is gonna be the summation of K of, what is the BT? So that's gonna be BTij times AT, I'm sorry, not J, K, KJ, right? But that's gonna be the same as, what is a BTIK? That's a BKI, right? Because that's the transpose of the original. So, and this is gonna be AJK, right? So that means the AJK, BIK, so that's gonna be, what? Given that this is defined this way, this is a C, um, this is crazy. Uh, Apple product seems to getting bad every year. I screwed up somewhere right here. CJI, right? So for CT, that is the CJI. So we get that identity here, right? So this is the end of the proof. Something like that. So, I mean, so this kind of a basic proof, I expect you to know. You see what I mean, right? So that means it can be on the exam, right? So now we're going to define the inverse. All right, so before we define an inverse, what kind of properties does the A inverse has? So that's something we need to know. So by definition, we want this to be identity matrix, right? So this is more like a definition, okay? So we can call it left-hand side inverse because A inverse is multiplied to the left-hand side, right? So let's say this is the matrix. And so this one, I'm not asking matrix A to be a square matrix, right? So even for a non-square matrix, we can potentially define A inverse, right? See what I mean? So for example, if A is 3 by 2, then we can have A inverse such that, I'm not sure if it exists, but if it exists, we can define, um, maybe we can find A inverse like that, right? So this is a definition, not relying on the dimension. But for now, for this course, we're just gonna stick with the convention that A is a square matrix, right? So this, what's the next thing we need to show? So we need to show is, so this is we need to show, right? Or we want to find the answer if this is the case or not, right? So is the left-hand side inverse the same as the right-hand side inverse or not? So in real number, we don't have to worry about that, right? So the multiplication in real number is commutative. The order doesn't matter. But in matrix algebra, the order matters. So maybe uh, they're not the same. But the short answer is they're the same. Okay. So, so this is a proposition. So this is a proposition that they're all the same. So of course we need to prove it. Um, Proof is not, actually not so difficult. So so let's say um, um, this is the right-hand side inverse matrix. Okay, so let's say this is the right-hand side inverse matrix of A. So that is I, right? So you multiply A inverse to the left-hand side this way, right? So you multiply the A inverse on the left-hand side of the equation, okay? Then we know that this is again A inverse from the property of the identity matrix, right? So that means A inverse times I is, no, sorry. I screwed up here. Okay. So, but A inverse A times A right-hand side matrix is the same as this one. So we already proved that before, or we're supposed to prove it. I'm recording today's lecture, so you don't have to record it, okay? Because there is another COVID patient. So, and I'm gonna upload it. So that means I times AR inverse, right? Which is, but this is A inverse. So that is AI inverse. So we show that left-hand side inverse and the right-hand side inverse, they're identical. Okay. Ah, these are kind of basic proofs. Yeah, I know you ask. I know at least one of you will come to me and ask this question. Why do I have to know the proof? You don't. You don't have to know the proof for economics per se, for the economics you're gonna do per se. But one of them might need it. And even if you don't need it, going through the proof makes you fluent in mathematics. All right. So this is all practice. Even if you don't use it in the future, you sometimes practice it, right? All right. So that's the property we know of. And we know a few more properties like uh, 413, equation 413, like A inverse is A. So this is again easy to prove. Um, 4 times 1, 4. AV inverse is B inverse A inverse. All right, and transposes inverse is the inverses transpose. All right, so so the proofs are in the textbook, so you might want to check it yourself whether you can follow the proof or not. Okay. Might be on the test, or I don't know, might be on the homework. Yeah, I'll probably give you homework by the end of the next week or in 2 weeks. I'm not sure. Yeah. All right. So now I'm gonna give you the. So I'm gonna skip the section 4.7. I might come back, but for now I'm gonna skip it. Yeah, I'll probably come back. So so I'll give you an answer. Without the proof what the inverse matrix looks like, okay? But before defining the inverse matrix, I'll first, so remember, this is our ultimate goal, right? Solving this equation, right? But we know that, um, but we know we require a certain condition, right? So the condition is that, so basically the fact that we have this solution means we know how it looks like, right? So we talked about this one many times, right? So how you find the route from one point to the other point, right? So what is the requirement? The requirement was the three columns in three-dimensional space, the three columns should be different enough, right? So I'm gonna characterize that condition first of all. So the condition we'll say is that the three columns are very different. Okay. So I'll give you an answer without the proof for now. Um, so So this is x1 times a11, a21, a31 plus x2 times a12, a22, a32 plus x3 times a13, a23, a33, right? So we need these three vectors to be very different from each other, right? So to give you an answer, so in other words, um, the the three vectors are not in one plane, but each pairs should make different planes, right? So that is the requirement, right? So the answer is the following. So so-called determinant of matrix, um, no. So we're going to define this one. So that is, but before defining this one, we're going to define determinant of A11, A12, A21, A22. All right, so I'll use the different characters. So let's say alpha, okay? So, so let's say this is one number. So determinant of this one is just the number itself. So we know that this not being zero gives you the condition here, right? Because that's something we already know, right? A times x equal to b has a solution given that a is not zero, right? So this was an easy condition. So what will be this one? So we already know the answer, right? So what is the answer? Alpha 1, 1, alpha 2, 1, alpha 1, 2, alpha 2, 2 equal to 0, 0. When does it have a, well, it doesn't have to be 0, but when does it have a unique solution? So for B and B1 and B2, yeah, so they have to be different lines, right? So that means the ratio between these two has to be different, the ratio between these two, right? So that is what you learned in junior high school, right? It's nothing new. This is from junior high school, right? So what I need is that alpha 1, 1 over alpha 1, 2. So that's the slope of a straight line, right? It's different from alpha 2, 1 over alpha 2, 2, right? So I'm going to write it down different way. That is alpha 1, 1 times alpha 2, 2 minus alpha 1, 2, alpha 2, 1 is not equal to 0. Okay? So that's how we're going to define the determinant. That is alpha 1, 1, alpha 2, 2 minus alpha 1, 2, alpha 2, 1. Right? So if this is not 0, we have a unique solution for the equation. Suddenly confused? So this is a system of linear equation, right? Yeah? This is a system of a linear equation that you learned in junior high school. I just wrote that using the matrix. But you know this equation, right? And in junior high school, we learned that this will have a unique solution when the slopes of the two straight lines characterized by the first equation and the second equations are different, right? So in other words, this was the condition for the unique solution. Okay, since you're not giving me any reaction, I'm not sure if you're following me or not. Raise your hand if you're not following me. Raise your hand if you're following me. All right, so what's the other option? It's like the quantum mechanics could be or could not be following me. So x2 is minus alpha 1 over alpha 2 x1 um, plus b1 over alpha 2. So that's the equation, right? Describing the first equation, right? So y is slope times x plus a what's the one? What's the word? I forget what it is, right? So if the two equations have different slope, we know that there is a unique solution. And this is the condition for the different slope. So, and which is the same as this condition, right? So I'm just multiplying alpha 1, 2 times alpha 2 on both sides, and I get this one. Do you see that these are the equivalent? Yeah? All right. Um, I mean, in a sense, this is more general, right? Because this requires that neither of them is zero, right? But this one, even if one of them is zero, this can be still stated. And this is actually the real statement, whether they're perpendicular, or, whether the slopes are different or not. So this is the definition of the determinant for the second dimension. This is the definition of the determinant for the first dimension, which is, very, very trivial. So what's the definition of the what am I doing here? So the definition is the following. So so first of all, I'm gonna take a look at A11 and look at the matrix here. All right. So that is A11 times determinant of A22, A23, A32, A33. And next, you see this number and look at this matrix. All right. So A12 times determinant of a smaller matrix, smaller square matrix. You see that? So this is the same as the left-hand side. This is the same as the right-hand side, right? And then the third one is supposed to be green, but it's not really green enough. It's okay, looks green there. A13 times determinant of A21, A22, A31, A32. And then times minus 1, 2, 1 plus 1, minus 1, 2, 1 plus 2, minus 1, 2, 1 plus 3. And you add them up. Okay? So this 1 and 1, I'm referring to 1 and 1 here. 1 and 2, I'm referring to 1 and 2 here. 1 and 3, I'm referring to 1 and 2, 3 here. Okay? So 1 plus 1 is this one, 1 plus 2 is here, 1 plus 3 is here. All right? So this is how you define the determinant of matrix. All right? And if this is not 0, then we have an inverse matrix. Okay? So in other words, if this is not 0, that means that the system of linear equation has a unique solution. All right. So it doesn't tell you what the inverse matrix looks like, but it gives you a condition whether the three vectors determining the linear equations are different enough from each other. So in other words, these three vectors can be used to reach any point in three-dimensional space. So this is the condition. Why this is the condition that requires much more time than I have for this course. So I'm not going to explain that, but you sort of see where it comes from. Um, did you learn inner product in high school? No? So that means you never learned outer product either. All right. Okay. Yeah, we'll get to that. Okay. So this is the condition for the three vectors to point very different directions. And it turns out that determinant A21, A22, A23, A11, A12, A13, A31, A32, A33. Okay? So if this determinant is non-zero, okay? So if this is non-zero, does it mean that this matrix, this determinant is non-zero too? What do you think? So this one, I just swapped the first row and the second row. All right. So do they give you? So if this is non-zero, is this going to be non-zero? Think about the geometry. The system of equation given by this matrix, system of equation given by this matrix, they're the same. So if this is non-zero, then this should be non-zero because the system of equation given by this matrix has a unique solution. So, and this gives you exactly the same system of linear equation. So it should give you a unique solution too, right? But what does it mean? That means I can rewrite this one in terms of A to 1, A to 2, and A to 3, right? So in other words, A to 1 times determinant, determinant A12, A13, A32, A33, minus A22 determinant A11, A13, A31, A33, plus A23 determinant A11, A12, A31, A32. They have to be give you the same number except the sign, maybe. Okay. So in fact, we can verify that this is the same as the above with the multiplication of a -1. All right. So if you actually expand it, if you expand all the determinants, you can show that very easily that this is the case. So in general, determinant of a matrix Aij. So here's matrix Aij. So let's think of a element Aij, a component Aij. Then you have a submatrix composed of these red squares, right? So you add this red squares, you get a matrix of m minus 1 times m minus 1, right? So I'm just removing a column and the row, all right? So matrix where one column and one row is removed, that will be matrix of n minus 1 times n minus 1, right? When this is a matrix of n times n, okay? When this is n times n, we can think of this one. So this matrix is called, what's the notation they use? It's called matrix Mij. So what's the word? I think this is called a minor. So this is called a minor. So we can think of this matrix Mij. So the first definition we looked at here is that determinant of A is the summation of A1. Okay, so let me just write down element by A1 1 times determinant of M11 plus minus A12 times determinant of M12 plus A13 determinant of M13 and so on. Okay? Minus A14 determinant M14 and so on. Okay? So you see this alternating signs here, right? So which were given by these here, right? Okay. So in summary, I can rewrite it as A1k times determinant of M1k 2 times minus 1 to the power of 1 plus k. So k is 1 to n. So this is the determinant of A. But what we have just shown is that we can alternatively define determinant as A21 times determinant M21 minus A22 determinant M22 plus A23 determinant M23 and so on. Okay, so I can use the second row to define the determinant. A2k determinant M2k times minus 1 to 2 plus k. Okay, I'm sorry, so it should start with a minus sign, actually. All right, so this is a small minor point. So even though we started with the definition of determinant using the first row, from the observation of the geometry where it's coming from, we can see that, in fact, we can define the determinant for any rows. Okay. Moreover, we can even define it on any columns as well. So in fact, we're following the rows and finding the minor matrices, and multiply them with the determinants of them. But we can do the same thing for the columns as well, and that will give you the same number. So I'm stating it without the proof, of course, now. That will require much more time, so I'll just state it. You have to trust me. So first of all, so if I really, in terms of a row, the generalization is you can choose any row to define the determinant. So here I'm picking up row I, and this will be the general formula. So this is the same for any I you choose. So for any row, you can get the same thing. So I'm just gonna state it without the proof that you can do the same thing for any column. So for any column J, this will define the same determinant. Okay. All right. What else? So it takes time to get used to it, to compute it. It takes time to compute it, but I'm sure you'll get there. So let's give you an example. So this is from, so sorry, this is just a determinant, right? So now we're going to find out uh, um, the inverse matrix. So I'm really bad at names. Okay, adjacent matrix. All right, so we're gonna find the adjacent matrix that is composed of. All right, so I need to define first something else. So this is called cofactor. So cofactor is denoted typically by Cij. All right, so that's it's the same as determinant. I'm sorry, not determinant, but it's the same as Mij, but except that there could be negative sign in front of it or not. Okay, so we already defined what minor is, right? So this is the matrix A where ith row and j's columns are deleted, right? So this cofactor is basically the same matrix, but sometimes negative one is multiplied, the other times it is not. Is it defined that way? Yeah, okay, right. That's right. Yeah, okay. And to save the space, from now on, I'm gonna write it down as this way. Okay. So this is just to save the space. So this reminds you something, right? So what does it remind you? Ax equal to b is the solution is if a is not 0, right? Okay, so you can think of that way, but anyways, this is the notation we use. So we use this absolute value notation to denote the determinant of matrix A. Okay, so it's just a different notation. All right, so adjacent matrix A is a matrix of C11, C21, C31, CN1, and C21, I'm sorry, not C21, C12, C1, C22, C32, and so on. Right, so here will be CNN, and here is a C1N. So as you noted here, the indices are reversed. Can you see that? So typically, so for the second row, first column element, we're taking the cofactor of the first row and the second column. Okay, so So how do I say that? So I'll give you an example. So let's say 1, 2, 3, 4, 5, 6, and minus 0. Okay, so let me see. 2, 1, minus 1. Okay. So these three vectors are linearly independent. So this is an invertible matrix. Don't ask me how I know that, but I know that. Yeah. So the minors, so the cofactors are, so C11, C12, C13, C21, C22, C23, C31, C32, C33. All these are matrices, right? Smaller matrices, right? So C11 is gonna be what? It's gonna be minus 11, right? No? Okay. 5 times minus 1 minus 6 times 1 minus 11. Okay? Because C11 is this matrix, right? And C12 is going to be the matrix of what? 4, 2, 6 minus 1, right? You deleted the first row and the second column. You deleted the first row and the second column, and the remaining is the matrix cofactor. Actually, I need to multiply minus 1 to 1 plus 1. Doesn't matter. Right? So what's gonna be? That's gonna be minus 4 minus 12 times minus 1. So that's gonna be 16. All right. So what else? Let's just do the random things like a 3, 2. That's gonna be here, right? Maybe I'll use different color. This one, right? So that means here, this is going to be matrix 1, 4, matrix 3, 6, minus 1, 2, 3 plus 2. So that's going to be 6 minus 12 times minus 1. So that's going to be 6. Okay? So you can compute all these things. So putting them in this way, so if I plug all the numbers here, what I get is I hope I'm fast enough. Minus 11. No, this is not adjacent matrix actually, is it? Yeah, it is. Right. So minus 11, and C12 is 16, and C32 was 6, and C21 is okay. C13 is 4 minus 10, so that's going to be minus 6. C20 is minus 2, minus 5, but I need to multiply minus 1, so this is minus 1, minus 6, so minus 7, and this is 1 minus 4, so minus 3, but need to multiply. No, sorry. Do I multiply? No, no. Yeah, I should multiply. It should be 3, right? Yes, 3. And the one is 12 minus 15, so that should be minus 3. And the other is 5 minus 8, so it should be minus 3. So this is the matrix. But this is not adjacent. Bottom left. No. No, I don't think so. This is 5 minus 8. So that's minus 3, right? So, right, you're right. Yeah, so that's minus 3. And minus 1, 2, 3 plus 1 is 1. So should be minus 3, right? So, so if you like, you can think of this table plus, minus, plus, minus, plus, minus. Okay? If you understood this table, then you understood what's going on. If you're not, you should make harder effort. So anyway, but this is not adjacent matrix, all right? Adjacent matrix is the transpose of this one, right? Because see, the indexes were different, right? So the adjacent matrix of A is gonna be minus 11, 16 minus 6, 5 minus 7, 3, minus 3, 6, and minus 3. So this is adjacent matrix, okay? So which is um, C11, C21, C31, C21, C12, sorry, C12, C22, C32, C13, C23, C33, right? So see, this is different from this one, right? They're different. They're not the same, right? So this is the transpose of this matrix, okay? So the index is following the original matrix A, but you need to transpose it to find the adjacent matrix, right? So now that we have this adjacent matrix, let's multiply it with the matrix A, all right? So the initial matrix was A11, A12, A13, A21, A22, A23, A31, A32, A33, and then C11, C21, C31, C12, C22, C32, all right? So let's multiply them, see what it comes out. So the first, you multiply, okay, the first column as first row with the first column. What do I get? That looks familiar, right? If you multiply these two vectors, what do you get? You get the determinant. So that is the formula for the determinant, right? So that's the determinant of A. And if you multiply the second row with the second column, what do you get? It's again the same thing. It's the determinant you defined. So this is a determinant in terms of following the second row, right? So if you define, so where is it? So this was the determinant of A following the second row, right? So it's the same thing. And the last row with the last column, we get the determinant of A. Okay? So that's amazing. At least on the diagonals, it's amazing, right? But how about the other parts? So this one is, how do I get it? This one is first row with the second column, right? So if the first row was this one, then you will have no problem. That will be, again, determinant, but it is not. So that looks like a problem. Um, but the answer is they're all going to be 0. And how do I know that? Because A11, C21, A12, C22, A13, C23. This is a determinant of, so this will be determinant of what? Um, so this is erasing the, following the second row, right? So A11, A12, A13, A31, A32, A33. So these 6 numbers will determine this determinant of cofactors, right? Yeah. But what are these A11, A12, A13? So this is essentially the same as the determinant of this matrix, right? So if you think of determinant of this matrix following the second line, this one times matrix A1 to A3 to A1 3 A3 2, which is this one, right? And this one times matrix A11 A13 A31 A33. I mean, of course, I need to multiply minus at the appropriate places. So it turns out that this number is the same as the matrix of this matrix, determinant of this matrix. And I know that this determinant is 0. How do I know that this determinant is 0? The rows are the same. So why does it imply that determinant is 0? 한국말로 해. 왜 unique? Why doesn't it have a unique solution? Yeah, exactly. So if you think of a geometric meaning behind the matrix, this is just 2 equations in 3-dimensional space. So we're not going to have a unique solution, right? To have a unique solution, the minimum requirement is we need to have 3 equations, 3 variables, right? But this matrix gives you 2 equations with the 3 variables. So we're not going to have a unique solution. So that means determinant has to be 0. So we know that this is 0. And the same logic will go on for different places. So they're all going to be a determinant of a certain matrix with the same rows or the same columns. All right. So we know that it looks like this. And this looks like what? This looks like identity matrix, except that it's multiplied by determinant, right? So that is determinant of A times identity matrix. So we just found that the inverse matrix, that is what? So A inverse is going to be 1 over. So if we pre-multiplied 1 over determinant of A, then we get the inverse matrix. All right. So that's the answer. So this is the inverse matrix. So so if you want to make it more, I don't know, rigorous, so let's say Bij, then Bij is 1 over determinant of A times cofactor CJI. So this is the inverse matrix, right? So getting that 0, if you have a proper geometric interpretation, getting that 0 is very easy, but takes time. So I want you to, I mean, there are many steps we omitted to get here that I stated without the proof, but I want you to know this proof. Okay, this is really a basic thing. So this makes it, yeah, again, you will never use this proof ever in your life, but that makes you more acquainted with the matrix algebra, basically. Okay, that makes you more dexterous in terms of dealing with the matrices. All right, so this is the inverse matrix. So previously I claimed that this was the case. Do you remember? All right. So so this is again easily shown once you know the inverse matrix. Okay, so this is not what I was going to say actually. Sorry. All right, so I'll just see how much. Yeah, so basically the rest of it of chapter 5 is just application of the this inverse matrix. So, oh shit, I have only 2 minutes. All right, so I'm a little behind the schedule. But anyway, I'll stop here. I'll see you next week. So this Thursday, there is no lecture. There is no offline lecture. I'll upload the recordings. I know. Again, by the end of the Friday, I'll do that. Yeah.